This video will be on section 5.2, integration with substitution. So the main topics in this section we'll talk about the formulas associated with integration by substitution. This is what we'll see very quickly is this is like the chain rule but for integration. Then we'll just practice like we did last section, doing general antiderivatives, so just integrating, getting r plus c. And then we'll do some specific antiderivatives, meaning we'll solve for c and using substitution. All right. So substitution really pops up. It becomes necessary if you can't do what we did last time. All right, so I'll remind everyone, the goal of last section was to use our integration rules to make the inside of the integral just a power of x, or e to the x. Then use the appropriate formula. So either the power rule or the e to the x rule or the one that came out to be the natural log. You'll notice that the formulas that we have here below for those three replacements are exactly the same. The idea here, though, is that very often when we use substitution method, I don't know why the letter chosen to use is u, but what we'll do is to make our thing look like a power of x or a power or e to a power, is we will set u equal to something so that we can get to the same format as having a power of u or e to the u inside. Then we will use our appropriate formulas. Now, one thing to point out here with these formulas that's very important is when we plug in for u, so you'll see very quickly with an example, you have not only u to plug in for, but you have to do something with the dx to make it du. So we'll see with the substitution method is what's going to happen is we're going to pick u, then do the derivative. So du over dx equals the whatever the derivative formula is. Right, so we're still doing derivatives, and then because we want to plug in for dx to replace with du, what we do is we solve for dx and plug in. All right, this will make more sense, but I like to overview what we're doing first, especially when it comes to substitution, because it does break down to being very similar to last section. This extra thing is the part you have to get used to. All right, so we will find the indefinite integral and check the result by doing the derivative. All right, this is just for practice. It's been a while since, maybe not a while because you just had to test with derivatives, but one thing I don't want you to forget is all those derivative rules, because they do pop up when you integrate with substitution, which is rather frequently. All right, so the first thing here is we want to integrate our function. Let's not worry about checking the result yet. So we want to integrate 1 over 3x, 3 plus 5x to the 6th times 30x to the 5th dx. All right, now the reason we need substitution here is that there is no way to simplify this to just a power of x or e to the x inside. And really, that boils down for one reason, and that's because the denominator here is something that has a plus or a minus in it. You can't break up a fraction with a plus or a minus. So that's going to be a dead giveaway in a lot of our problems. All right, the denominator cannot have a plus or a minus in it when we want to integrate. All right, so the replacement, the idea here is that if you do have a denominator with a plus or a minus in it, is you let u be the entire denominator. Okay, you'll see why I'm not really focused on the 30x to the 5th right now part is that'll get taken care of in a minute. What we want to do first, the method of integration, is figure out our u. Our u is going to be 3 plus 5x to the 6th, and I forgot to write 3 in front. U is the entire denominator, 3 plus 5x to the 6th. And then the reason why we have to do this extra step of doing the derivative is when we have a u here, we cannot have u's in x's. You can only have one letter. So we're going to have to do the derivative right? Like I mentioned above, we figure out u, we do the derivative of u. The proper formula, du over dx, equals the derivative of this would be 30x to the 5th. Right, so remember, derivative is our old rules. The derivative of just a number is 0. The derivative using the power rule is we bring the power down and then subtract 1. And then what we're going to want to do here, this is my preference. You might see it done other ways, but this way always works, is this equation, solve it for dx. Right? And it'll be pretty straightforward when you solve for dx on how to plug in everything and simplify. All right, so let's go ahead and do that. I'm going to rewrite the equation we have. All right, now even though this represents like du over dx, a derivative, you can multiply each side by dx. So we get du equals 30x to the 5th times dx. You know, sort of think about du and dx as their own letters. Like if this was x over y and you had a z or something, 3 different letters, you're solving for one of them. And now to finish up getting dx by itself, we divide each side by the 30x to the 5th. And our formula here, when we solve for dx, we get du over 30x to the 5th. Right, and I'm just going to write it up here so we can see the problem along with what we have. All right, so to recap, the starting point of doing integration with substitution, you figure out your u. This is one way to choose u, but this is a foolproof way. If you do have a plus or minus in the denominator, 99% of the time, you're going to choose u this way. And then dx, we do the derivative to get du over dx and then just solve that for dx. Right, but now what we do is we plug in all right, so what I mean by that, I'm going to rewrite the integral first. We got 1 over 3 plus 5x to the 6th times 30x to the 5th dx. And when we plug in, the denominator is what we made u. And then, even though we have a 30x to the 5th in the dx part, I'm just going to leave that alone. I'll show you what happens. The reason we solve for dx is now we can plug in what dx is. Dx is du over 30x to the 5th. Let me go ahead and put this pink in u, or this u in pink. So you can see what we did. Where I saw the 3 plus 5x to the 6th is where I put u, because that's what we chose. And then for the dx, the formula that we got, that's where I plugged it in. Now this is why the 30x to the 5th is here, is when you plug in, all x's must cancel. If they don't cancel, you either have to rearrange it in a way that they will cancel, or you did something wrong. But here, they cancel perfectly. Actually, we don't even need the 30s to match to get the x's to cancel, but that just happens to match. And when we do that, so these two cancel. And what are we left with? We're left with 1 over u and d times du. Right? All the rest is gone. And this is something we know how to integrate. This is just a power of u. Imagine if we had x and dx, same idea. The integral of 1 over u du is the natural log of the absolute value of u plus c. And then the last and final step, once you're here, you've done 99% of the work. You just don't want to forget this. After integrating, plug back in what u is. So a good thing to remember is since we started the problem with x's, we want to end the problem with x's. Right, but once you do that, like I said, it's pretty direct here. So we got the natural log, the absolute value of u, which is 3 plus 5x to the 6th plus c. And that's our final answer. Okay, so once again, the first thing you're going to have to do going forward after this section is, am I going to use substitution or not? One way to know you're going to use substitution is if there's a plus or a minus in the denominator, and that tells you what to make u as. All right, then when we use substitution, we've got to do the derivative and solve for dx, plug in our stuff here. If everything cancels out well, like it did this time, then we should see a pretty straightforward formula pop out. But what I'll do is you can check the derivative of this by using the chain rule. Since you use substitution when you use the derivative, you're going to use the chain rule. The derivative of our answer here, we get 1 over the inside, because it's a natural log, 1 over the inside, times the derivative of the inside from the chain rule, which is that 30x to the 5th. And then derivative of a number is 0. And what you'll notice is that the derivative is exactly what we started with inside, so we do have the correct answer. All right, so that's one thing to keep in mind as far as integration when we want to use substitution. The second one here, I'm not going to do the derivative part at the end for all of these. You can check using the derivative, doing the derivative for any integral. But this one here, we want to integrate s to the 8th power plus 9 squared times s to the 7th ds. Now, why do we want to use the substitution here? Why not just try to break it apart? Well, we could square this part out to get rid of the parentheses and then distribute the s to the 7th through, but that's going to take a while. And if this power was changed to like 5 or something, then it would be very challenging. Right, so another thing to look out for with substitution is if you have something inside raised to a power that's not just s, or, you know, if it was just s to the 8th squared, we could simplify it, but the plus 9 makes it more challenging. Sort of like when we did the general power rule, the power rule with the chain rule. That's going to be the indication we want to use that as u. Right, so for this one, my u is going to be s to the 8th plus 9. Because if I do that, then this just becomes u squared, and that simplifies it quite a bit. But once again, we cannot forget about the derivative. Now, one thing I'll mention here, the first step if you write it as du over dx or whatever, the first step is always going to be multiplying to get rid of that fraction. So you can take a little shortcut and just write du, do the derivative of u. The derivative of s to the 8th plus 9 is 8s to the 7th, and then ds. Right, so instead of writing du over ds equals this, we can just start right here because we're going to solve for ds anyway. All right, but now we're going to repeat the same steps. We're going to solve for ds because we only can have u's after we do substitution. We divide by the 8s to the 7th. And what we're going to plug in then for ds, we get du over 8s to the 7th. All right, so let's go ahead and plug that in. S to the 8th plus 9 is what u is, so we get a u squared. The s to the 7th, even just like last time, it should go away and cancel out at the next step, but we're not doing anything with that. And then for ds, we're plugging in du over 8s to the 7th. And just like last time, all the s's should cancel. We only want u's left. And that will happen. S to the 7th and the s to the 7th will cancel. Like I mentioned last time, the numbers don't have to match. So we have an 8 here and we don't have an 8 here, but that's okay. And let's just go ahead and write what we're left with. So we've got a u squared. The s to the 7th is gone in the top and bottom, and we got a du over 8. Okay. Now this is pretty much at the point where we can integrate this 8. It doesn't matter that it's written over an 8 because this is, written over du, because it's all multiplication. If it was over the u squared, you would do the same thing as if it's over the du. We bring it outside. And because it's in the denominator, it's not going to be 8 outside, it's going to be 1 over 8. Right, so we've broken down our problem to be 1 over 8, and then we want to integrate u squared du. And because the u's all match, everything's a u inside, we just do our normal integration. We add 1 to the power, divide by the new power, and we get our plus c every time we integrate. And then the last thing to do is plug in what u is. This is probably the easiest thing to forget when you're starting this is you get here, you integrate. But because we started with s, our final answer must have s in it. So the top here would be 1 times u cubed, which is u cubed, but u is s, so we get u is s to the 8th plus 9. So we got that cubed over the bottom. 8 times 3 is 24 plus c. And we've integrated, our integral sign's gone, we only have s's left. So that is our final answer. Now it is good practice if you want to do the derivative here, do the chain rule, and see that you actually do get s to the 8th plus 9 squared. You can see how that would sort of work because we'll subtract the 1 from the power, and then an s to the 7th on the side from the chain rule. All right, number 3. When you're integrating something with e in it, it's very often the easiest one to figure out how to use substitution if you need it, because if it's not just x or whatever your letter is, you're going to replace the exponent with u, because we only know how to integrate e to the x. All right, and since we have x cubed, not x, in the exponent of e, we use the exponent for u. All right, so we're going to have u equals x cubed. And that goes for anything. It can be x plus 1, or 2x. It doesn't have to be a different power. Just as long as it's not exactly x, that's going to be what you choose for u. And then du, the derivative of x cubed is 3x squared dx. Solve for dx. I divide by 3x squared. We get du over 3x squared equals dx. I'm just going to rewrite this so I have room to write. But what did we do the previous 2 times after we figured out u and dx? So we plugged them in. All right, so we're not actually, oops, forgot my dx. We're not actually plugging in anything for x squared. That's the part that's hopefully going to cancel. Then we got e. In place of x squared, we have u. And then for dx, what we plug in for dx is du over 3x squared. Now, once again, everything that's not a u should cancel. Well, the x's here, the numbers, as we saw last time, that's fine. But all the x's must cancel. And you will see that they do cancel. We have an x squared on the top, x squared on the bottom, which do. That means we chose the right thing. All right, so what we're left with, we have e to the u inside, and then a du over 3. Now, just like last time, we know how to integrate this with the 3's not there. So if you want to take that step and factor or bring the 3 out, remember, since it is in the denominator, it is a 1/3, not just 3. And the integral, since it's just e to the u, du, everything is a u, we get itself plus c. We've integrated, we still have the u, so the last step, plug back in what u is. U is x cubed. And once you do that, you are done. But once again, I can't emphasize enough, it's just the same steps over and over again, looking for the right things so you know when to actually do substitution. You don't want to think about going forward, every problem needs to have substitution in it. If you try to do substitution when you don't need it, you can still get it right, but you'll pretty much be replacing u with x in problems and not changing it at all. So the number 4 here kind of combines numbers 1 and 2 that we did together, but it really, I just want to emphasize, you're looking for the same thing. Why would we need to use substitution here? Well, there's actually 2 reasons, but they kind of get brought up together. We have a plus or minus in the denominator, and we also have a plus or minus thing being raised to a power. Either one of those things tells you, make the inside u. All right, so this one we need substitution again. Plus or minus in the denominator is one reason. The other reason is plus or minus in something raised to a power as well. Either one of these tells you you must do substitution. And we make the inside equal to u. Now you don't want to do the whole denominator here. You don't want to include the cubed part because if you do, you won't get the cancellation, but it's not necessary because if you make the inside equal to u, then you'll have just u cubed down here, which is fine. All right, so kind of think about it like, well, we see the plus or minus in the denominator, so we want to use the denominator, but because there's a power here, we only want to use the inside. Okay. We figured out what u should be, 4 minus x to the fourth, the inside. Then du, we do the derivative of this, which is negative 4x cubed. Then we have our dx. And then we solve for dx. So we've got dx equals du over negative 4x cubed. We figured out what u and dx should be. Now we plug them in. But I'm just gonna rewrite it first, like I have been, so it just looks like it's all in one line. All right, so we integrate. We're not plugging in anything for x cubed. That's once again going to be that thing that we hope cancels out. We are plugging in the 4 minus, oops, I wrote that backwards from the original problem. It's 4 minus x to the fourth cubed. So the inside here is u. And we still have that third power. And then in place of dx, we have du over negative 4x cubed. Once again, we're at this step where we plugged in. Now all the x's should cancel. And they do. We have an x cubed on the top and an x cubed on the bottom. So what are we left with? Well, this is a 1, since the whole thing went away, over u cubed times du over negative 4. Right. We've gone through this pretty much every time that we've done this now. We can pretty much integrate this. We do have to adjust the u here because it's a power of u on the bottom. We need to move it to the top to make it a negative exponent. And we should also bring the negative 4 out. All right, so when we do that, 1 over u cubed becomes u to the negative 3. The negative 4 on the bottom becomes a negative 1 over 4 outside. And then we're left with the du. Now we can integrate it. We have just a power of u inside. It's not negative 1, so we're going to use the power rule. And so if we add 1 to the power, negative 3 plus 1 is negative 2. We divide by that new power. Then we write our plus c. Right, and then to finish it up exactly like the other ones, we just want to plug in u. Now the negatives here are going to cancel because it's all multiplication, so I'm going to knock that out. And if you don't like the negative exponents, you can leave it there or replace it. I'm just going to change u first. So we got u to the negative 2. U was 4 minus x to the 4th to the negative 2 over 4 times 2 is 8 plus c. And if you don't like the negative exponent, you can bring this down to the bottom and make it positive. That would leave a 1 on the top because you brought down the whole thing. And the exponent becomes a positive 2. Right, either one of these is correct. Like with last section, if you were to solve for c, you'd really want to do this second one because it's easier to deal with than negative exponents, but otherwise they're both the same. All right, so I believe we have 2 more here, and then we'll do just an example with a specific antiderivative using substitution, but it won't be any different, the method at least. All right, so number 5 here, we've got to integrate e to the 2x over 2 plus 9e to the 2x dx. All right, so this is kind of, for me, I would say it's the one where it could cause the most confusion because it conflicts with 2 separate rules. We have a plus or minus in the denominator, but we also don't have e raised to just x. So what do? Well, the more important thing is always to get rid of that plus or minus in the denominator. Right? It could be possible that you have to use 2 substitutions, but we're not going to even try to worry about that yet. The priority here is always the plus or minus in the denominator. All right, so what I was saying here, just to comment it, even though e is not raised to just the x power, don't use the exponent of e because the denominator is more important. And this is something that you have to work a ton of these problems to realize that's going to be the case. But we saw with the previous one as well, we kind of had 2 conflicting rules. So we use the whole denominator, just the power thing inside. We use just the thing inside. If we have a plus or minus in the denominator and e not raised to just the x, what do? We're going to use the denominator first. All right, so let's go ahead and do that. U is going to be the whole denominator. There's not an extra power on the outside, so we don't need to even question that. Then we do the derivative. Now the derivative of this, that requires the chain rule because we don't have just x in the power. We got our 9. The derivative of e raised to whatever is itself. But because of the chain rule, we also have to multiply by the derivative of the power 2x, which is 2. That is the chain rule. Right, now go ahead and solve for dx. If you want, simplify the 9 over 2 to 18. I'm just going to do it in one quick scoop. So we got 18e to the 2x to divide on each side. The 18 coming from the 9 and 2. And we have dx equals du over 18e to the 2x. All right, now let's go ahead and plug in our dx and our u like we have with all of these. Right, so e to the 2x on top here is not the thing we're plugging in for. That's the thing we hope that cancels out. The entire denominator is what we made u, so we're going to write it as u. And in place of dx, we're going to have du over 18e to the 2x. Now, if we chose right, everything with x should go away like it has in all of them, and it does. E to the 2x and e to the 2x cancel out. Right, so what are we left with when those cancel out? We have a 1 over u in the first fraction. In the second fraction, we have a du over 18 because the e to the 2x is gone. Then we can bring out the 18 like we have been. Since it's on the bottom, it's 1 over 18. And then when we integrate 1 over u du, that's our special power, -1, we get the natural log. So we have 1 over 18 times the natural log of the absolute value of u plus c. And then plug in what u is. 2 plus 9e to the 2x. And this is simplified. Because of the plus and minus inside of a log, you can't actually use any log rules here. It doesn't matter that there's an e there because of the plus. All right, so if you were to do this problem and not get it right, the homework would say exactly this. It wouldn't have a different form. All right, so this last substitution here, there is one problem. It's going to look like this, maybe one or two, I'm not sure. But when you make your choice for u, it's going to seem like you made the wrong choice, but I'll show you that it won't be the wrong choice. All right, so one thing, once again, we want to integrate x times the square root of x plus 8, and why do we want to use substitution? Why is it in this section? Well, the simple, quote unquote, simple reason is because the square root is the same as the 1/2 power. So I'm going to replace that. I never just like with derivatives, I don't like to integrate with radicals. I like to change them. And you can see what's wrong here is this breaks one of our rules. We have a plus or minus inside a power, so we need to do substitution. All right, and we let u equal the inside x plus 8. Then when we do the derivative of that du, the derivative of this is just 1. So we get du equals 1 times dx, and multiplying by 1 does nothing, so du equals dx. But we want to plug in our u and our dx, just like always. The dx out front we're not doing anything with yet. And then the x plus 8 is our u. That's being raised to the 1/2 power. And then the dx becomes our du. Right. But you see what's different about this one is there's nothing to cancel x out, at least in an obvious way. Since x doesn't cancel, there's only one thing you can do. It's actually from the equation you made from u, is solve u equals x plus 8 for x, then plug that in. Right, this is the one example of that, but it's good to see that it doesn't need to always cancel perfectly, and as far as on top and bottom of the fraction, it might cancel in this other kind of different way. So what I mean by solve for x is take your equation, subtract the 8 from each side, and we get not dx, just x. x equals u minus 8. And we want to plug that in for x. Like the only place we have x is right there. If we replace it with this, then we won't have any x's. So x is u minus 8. Then we got u to the 1/2 and du. Right. Now that we have only u's inside, we can go forth and integrate this. Now the first thing to do, because we have the multiplication, is to distribute the u to the 1/2 through. Because once again, we don't have a multiplication rule for integration. We've talked about that before. When we distribute the u to the 1/2 to the u, we add their powers. 1 plus 1/2 is 3/2 minus 8. And then we multiply that by u to the 1/2. Since it's just a number, it looks exactly like it sounds. And then to finish up here, since we've done this a lot, we know we would break it apart, take out the numbers, but let's just do it all in one swoop. When we integrate u to the 3/2, we add 1 to the power. 3/2 plus 1 is 5/2. We divide by the new power of 5/2 minus 8. And then when we integrate u to the 1/2, we add 1 to the power. 1/2 plus 1 is 3/2. Divide by that new power of 3/2. And then plus c. Okay. Now finish up. We have a fraction in the bottom, so when we bring it up, especially since there's a number, not a number out front of the first one, we flip it and we get 2/5 because it would be multiplied by 1. In place of u is x plus 8 to the 5/2 minus 8. When we flip the 3 over 2, we get 2 over 3. The 2 times 8 is the 16 over 3. And then in place of u, once again, we got x plus 8 to the 3/2 plus c. And that is our final answer. Right, so like I said, there's only 1 or 2 of these in the homework, and that's it. And they look very similar, but it's good to know. When it comes to substitution, it doesn't always work out perfectly in the way the rest of them do. Most of them do, which is why most of our problems are like that. But some of them you have to do everything, and if it doesn't cancel out, what can I do to get rid of this x? Well, the only thing I can do is rearrange the u formula. All right, so we'll do one problem here, a word problem with specific antiderivatives, and you'll see when we have to go through and do the problem, that substitution method will be required. Right, but we'll go ahead and read it. It says the marginal price for a weekly demand of X bottles of shampoo in a drugstore is given by the function shown below. And so the price function is given here, but its derivative, its marginal price. What we want to do is find the price demand equation. If the weekly demand, let's go ahead and underline that. We want to find P of X, so we need to integrate. If the weekly demand is 150 when the price of bottle of one shampoo is $2, right? So this is telling us to integrate. This is telling us how to solve for C. And then the last question here is telling us to figure out something with our equation. And we'll leave that on the back burner for a second. But find the price demand equation. We need to integrate our derivative to get back to the original. So we got negative 9,000 over 3x plus 50 squared dx. We want to integrate that. Now, because of the substitution here, I'm going to take care of that first, just like I did with all the other. And after the substitution, we'll just see what to do from there. But why do we want to use substitution here? Because the denominator has a plus or minus in it. But because of the power here, we don't want to make the whole denominator u. We just want to use the inside. So u is going to be 3x plus 50. Just like with all the other problems, we got to make sure we get dx by doing the derivative. The derivative of u is just 3 dx. And divide each side by the 3 because we want to plug in and solve for x like with all the other problems. So du over 3 equals dx. And we're going to plug in just like before. And so we integrate the negative 9,000 is on top. That's not a part of what we're doing. Divided by, now the 3x plus 50 is our u, so we got 3x plus 50. And that is being squared. Oops, but the 3x plus 50 is u, so we should actually plug in u. And then dx, in place of dx, we got du over 3. Right, so we plugged in everything. Now one thing you'll notice about this one is that we don't even actually have an x left. So we're in a good spot already. We can simplify a little bit because the negative 9,000 over 3 simplifies to negative 3,000 over u squared times du. And then finish this up. As far as organizing it, we can bring the negative 3,000 out. And we know the u squared on the bottom, we can bring it up to the top, becomes u to the negative 2 power. Right, and now we can integrate it because we have just u to a power inside. So we add 1 to the power, which negative 2 plus 1 is negative 1. Divide by our new power of negative 1 plus c. And then since we're going to actually work with this one, we're going to solve for c. I'm going to simplify it. The negatives here cancel out. So we got 3,000. The u to the negative 1, we can bring the u to the bottom. It's just the first power, so we can write over u. And then to finish up, plug in what u is. Right. Always remember when you start with the letter in your equation, that should be your final answer's letter. So, and u was 3x plus 50. And so what we've got here, it's not the price demand equation specifically, it's the general one. So what did we do last section? After we figured out the general antiderivative, we then plug in our information. To solve for c. And that's what's in green above, so let's look at that. It says we want the weekly demand to be 150 and the price to be $2. Okay, now keep in mind the weekly demand is x. So it's saying plug in x equals 150. And then the price is what the actual equation represents, and we want the price to be $2. So we plug in x is 150, set it equal to 2, and solve for c. Let's do that. We got 3,000 over 3 times 150 plus 50. then plus C equals 2. Now the denominator there, 3 times 150 is 450, plus 50 is 500. We got 3,000 over 500 plus C equals 2. And luckily that comes out to be just 6. So we got 6 plus C equals 2. Subtract the 6 from each side and we get C equals -4. Once we found C, we would plug it into our price-demand equation up here to get our specific one. P of X equals 3,000 over 3x plus 50, and then C is -4, so we get a -4. All right, so we did pretty much the hard part. We figured out the price-demand equation if the weekly demand is $1.50 when the price of a bottle of shampoo is $2. And next it asks, what is the weekly demand when the price is $7.50? Let me go ahead and box that in to make it more clear. That's our answer. So what is the weekly demand, or what is X? That's what X is representing when the price is $7.50. Right, well, the price is P of X, so we plug in $7.50 for P of X, and we solve for X. Since we've already solved for C, we never have to worry about that again. Right, so to solve for X, I'll add the 4 to each side. That's probably the easiest thing to do first. Because if we add the 4 to each side, then we are in a place where we can cross multiply. But when you add the 4 over here, you cannot. Right, now to cross multiply here, the 1150, if you want, you can write it over 1 to see it more directly. So we cross multiply. On the left, we have 1150 times 3x plus 50. And on the right, we're multiplying by 1, so it doesn't change anything. We got 3,000. But we want to solve for x, so we'll distribute the 1150 through. 1150 times 3 is 3450 x. And 1150 times 50, I'm not sure on that one. Let's check. We get 575. Subtract the 575 from each side. So we got 34.50x equals 2425, 3,000 minus 575. And then to finish up, to figure out the demand, we divide by the 3450. And we get x equals 2425 divided by 3450. Oops. And we get about 70.289 or 70.290. All right, so what it says is if you raise the price of the shampoo to $7.50, you expect around 70 people to buy it. Right, but once again, you can kind of see the usefulness of integrating. Once again, as weird as it seems, figuring out the derivative, the rate of change of something is very common. Getting back to the original is what you want to do. Right, but that is our integration with substitution.